Welcome to the Deep Dive, our science corner. Today we're jumping into something invisible but truly revolutionary, X-rays, also known as Röntgen radiation.
That's right. And our mission today is really to get a quick handle on how they were found, the basic science, and importantly, why they matter so much.
So let's start right there. What are X-rays, fundamentally?
Okay, so think of the electromagnetic spectrum. You've got radio waves, light, UV. X-rays are up there in the high energy part. They sit between ultraviolet and the even more energetic gamma rays.
High energy and specific wavelengths.
Yeah, roughly speaking, between 10 nanometers and 10 picometers. The key thing is, compared to visible light, these photons pack a serious punch. A lot more energy.
Which brings us to the discovery story. 1895, Wilhelm Conrad Röntgen. It sounds almost accidental.
It really was. He wasn't looking for them. He called them X radiation because X for unknown, right? He was working with a Crookes tube. That's the device that makes cathode rays.
And he had it covered up.
Completely. Wrapped in heavy black cardboard to block any visible light. But then he noticed something odd. A screen coated with barium platinocyanide sitting nearby started glowing. Faintly green.
Even through the cardboard.
Exactly. Something invisible, something unknown, must have been coming from the tube, passing right through the opaque cardboard and hitting the screen. That was it. The aha moment.
And the practical use became obvious almost immediately. That famous picture.
His wife's hand. Hand mit Ringen. December 22nd, 1895. You can see the bones, the rings. Instantly, everyone saw the medical potential. It was huge.
Okay, so let's dig into the physics a bit. How does the imaging actually work? You hear about hard and soft X-rays.
Right. It's all about the energy of the photons, which we measure in kilo-electron volts, kVK. Hard X-rays have higher energy, say above 5 or 10 Ke. They're the ones that can penetrate deeply.
Which is what you need for looking inside things. Medical imaging, industrial checks.
Precisely. Soft X-rays. Much lower energy. They get absorbed really easily, even just by the air. Not so useful for seeing through stuff.
So for taking a picture of, say, a broken arm that's projectional radiography, you're using hard X-rays. And the bones show up because they block the rays more.
Well, they absorb them more effectively. It's not just about density that plays a part. The really crucial factor is the atomic number of the elements involved.
Ah, right. Bones are full of calcium.
Exactly. Calcium has a much higher atomic number than the carbon, hydrogen, oxygen that make up most soft tissues. So those calcium atoms are way more likely to absorb an incoming X-ray photon.
Creating a shadow, basically. A clear contrast on the detector.
That's the principle. Clear shadow where the bone is, less shadow where the soft tissue is.
But medicine's gone way beyond simple shadow pictures. Things like CT scans.
Oh, yeah. Computed tomography CT is a whole different level. It doesn't just take one picture. It takes hundreds of 2D X-ray images, slices from all different angles around the body.
And then math puts it together.
Sophisticated algorithms, yeah. They reconstruct all those overlapping 2D views into incredibly detailed cross-sectional images, or even full 3D models. Game changer for diagnostics.
And fluoroscopy, that's the moving X-ray, right?
Uh-huh. It gives you real-time moving images. Think watching contrast dye move through blood vessels, or guiding a catheter. Same principle, just continuous imaging.
It's amazing how fundamental they are, and not just in medicine. You mentioned industrial uses.
Definitely. Think X-ray crystallography. Scientists use X-ray diffraction, how X-rays scatter off atoms to figure out the precise arrangement of atoms in crystals.
Which is how we understood the structure of DNA, for example. Huge implications.
Absolutely. Material science relies on it heavily.
Yeah.
And, of course, airport security scanners. Using X-rays to see inside luggage, that's a very direct application of their penetrating power.
But that very power, the ability to penetrate matter, that's also the downside, the hazard.
It is. We have to be clear. X-rays are ionizing radiation. They have enough energy to knock electrons off atoms and molecules in your body.
Which can damage DNA.
Yes. And that damage can potentially lead to cancer over time. That's why their use is, and must be, strictly controlled. Shielding, dose limits, careful procedures.
And this danger wasn't something we only figured out later. People realized it quite early on, didn't they? Tragically so.
They did, sadly. Very early pioneers suffered. Clarence Dally, who worked with Thomas Edison testing X-ray tubes, got massive exposure and died in 1904 from radiation-induced cancers. Probably the first known fatality.
A terrible cost for that early exploration.
And Major John Hall Edwards, another pioneer in X-ray use, developed severe radiation dermatitis and cancer, eventually needing his arm amputated. So the risks were apparent almost from the start. It's always been a balance.
So wrapping this up, for you listening, X-rays are this incredible tool. Born from an accidental discovery, totally transforming medicine and science.
But always carrying that inherent risk, a constant balancing act between the immense benefit and the biological hazard, a true double-edged sword of science.
And you have a final thought for us. Something unexpected.
Well, here's something fascinating. We know X-rays are invisible, right?
Yeah.
But some early researchers, including Röntgen himself, reported seeing something when their eyes were dark adapted. A faint sort of blue-gray glow that seemed to come from within the eye itself when the beam was on.
Inside the eye,
Yeah.
not light hitting it.
No. It's now thought to be Cherenkov radiation. The X-rays pass through the fluid in the eyeball, moving faster than light in that medium, causing charged particles to emit this faint visible glow. A strange direct perception of these invisible rays happening right inside the observer's own eye. Something to ponder.